Okay, so I'll have, hi everybody, so I'll have the challenge to entertain you with a very exciting release talk after all these dull discussions about machine learning and artificial intelligence. Uh, just to, that some of you may not be aware of what GeantV is doing, so I'll try to briefly describe you what the project is about and what we're trying to solve here. So we all know that in the first phase of the LHC, basically, we have spent more than half of the CPU cycles for simulation-related tasks. And we also know that the luminosity will increase, and while the luminosity will increase, so that will the need of simulated samples. So we know that we will have some other competitors that will, like reconstruction, which will maybe take over the needs for computing, but that will still need a lot of simulation samples. And so that we are aiming for something, to put something in the simulation pipeline, some products that will be able to do a bit faster simulation. How we are going to do this? Well, the first aim was to profit better from technology, to be able to do more work with in the same amount of cycles, and that you can do, for instance, by doing an instruction level parallelism, vectorization, and stuff like this. But this cannot realistically gain you more than something like 3 to 5x. Okay, of course, if there is more to grab, we'll certainly go for it. But what we need is factor of 10 or more. So the solution can only come from a combined fast and full simulation. So what we will need is definitely faster full simulation, but also more fast simulation. More fast simulation, at the limit, people would say, why don't you do only fast simulation? You cannot do only fast simulation because, okay, we are not yet at the change of paradigm where you just replace the simulation with a black box, and then you just put in some event and then get out your article or whatever. So maybe this will happen in some future, but it's not the case. However, we want to really profit from machine learning and being able to do inference from sort of like generative networks into the as fast simulation module. So to have a sort of smaller black boxes inside the simulation engine to make it faster. Okay, so that's what GeantV is about. GeantV is about trying to combine fast and full simulation and trying to use more efficiently the existing resources and also be aware of the topology of the machines where we are running on. Okay, this is schematically describes sort of the basic idea. The basic idea is that instead of following particles one by one while doing the simulation in the full detector, you're trying to bunch particles together and group them into vectors and feed them as vectors to your computational algorithms so that you can put the loop there automatically. You know, optimization happens typically have a loop. If you are able to steer the particles in this way so that all the components of your framework benefit from multi-particle approach input, then you can hope of getting the benefits which are SIMD or instruction level parallelism and have better caching, hopefully. Now, there was a community review about this in the fall 2016, and the conclusion there is yes, there was this was a long R&D because it's not a simple problem; it's a complicated problem. And this came already with lots of byproducts which went back to the community, like VC, like Geom, like new physics models which were back-ported to GeantV and reintegrated for the user to benefit from. But really, we have to, not everything can be done by backporting some products. Some things is required, as you have heard previously from Liz, by changing some interfaces, changing some data models and structures. And the user will have to interact with it. Some of the benefits cannot be without that. So, but our belief is really that we have to give early a product to the community, even if it's not in the final phase, definitely, so that the users will be able to test it, to see the limitations and benefits, and to give feedback so that we can improve it. Now, talking about releases, so basically after this review, we sat down and we established, basically, it was a long period, but we established a work plan towards having some clearly releases. And the first release we call the Alpha release. It's coming at the end of this year, and it's aiming basically to allow the experiments to get acquainted with the framework and be able to build their own examples and do some physics, some shower physics, electromagnetic shower physics. In the beta release, which will be at the end of next year, we are aiming to having most of the final product and the performance of the final product. And here you have a list of how these features, what will be available at the end of the year in terms of features and vectorization, and what we expect for the next year. So now going a bit to the components to understand a bit how we improved, basically what is the final form of the product. It's a snapshot of what you're going to get in the Alpha release. I will go a bit through the components, and the first one that I want to talk about is the scheduler, which is aimed at orchestrating the particle flow to deliver all these vectors to the components, which may then be geometry or physics. And this was really gradually upgraded along the R&D. And now what we're going to deliver in the Alpha is the final version. Just to have an understanding of the challenges, so basically what we wanted to have was more like from something which steers vectors only to a component like geometry, because we wanted first to test to demonstrate the vectorization possibility with geometry. We had to migrate to a framework which is able to deliver vectors to the entire framework. And for that, what we did was just decomposing the algorithms which are behind the particle transport into what we call simulation stages. And these simulation stages can be geometry, and then inside the geometry simulation stage, you might have transport which can be vectorized, but only for a given volume. So you have to put behind simulation stages what we call handlers, which really are driving the data towards the components which are able to do the vectorization. So basically, we can put handlers here on top of volumes. We can put handlers on top of physics models, or whatever, magnetic field transport, or you name it. And what the handler have to provide is just a scalar interface and the vector interface. And the idea of the framework is that we should be able to enable for a given component vectorization just by switching on something that we call basketizing. That means you should see this particle flow coming from something that we call event server, which sends a stream of scalar particles to the framework. And then this stream is intercepted by all the simulation stages, which are the algorithm which are in your transport. And then a handler which will have behind the component which can be vectorized, has vectorized code, will start accumulating these particles and sending them only when you have what we call a full basket. That means a vector of a given size. And it will send it to the given component by a vectorized interface. What is nice about this schema is that you can accommodate in the same framework both a scalar and a vector flow. And you can allow a migration of the code from being scalar to being vector. And you can immediately test what is your performance gain when you do this switch on. I mean, as you can see here, you can start from a geometry stage and then select all the particles which go to different volumes. Some volumes are not interesting, and some others are, because there is a lot of simulation time spent there, okay? So you just vectorize some of those, and then you can run for those the vector code, and for the others the scalar code at the same time. Now we have tested a lot of features of this model compared to the previous version, and one of the main problems that we had to solve was memory, because since GeantV is mixing in the same simulation more than one event, the challenge was that the memory behavior was really explosive, like cascading, okay? If you were generating, in order to cool down an event, you have to basically simulate other 10 events, which is not the case now in the new framework, because we implemented a sort of a stack-like control using a special filter, which is which is put into the flow. And we are really being able to control now even for very large setups or very dense physics. In terms of scalability, things could go a bit better. Now we don't see a lot of difference when we profile for a given number of threads or twice the number of threads. That means that we don't have just bottlenecks. It's clear that memory operations come a bit high to the profile, and we expect this to improve while more physics code will become vectorized and available. Now, the prototype that we have now and the version that will be delivered in the alpha is NUMA aware, is topology aware. So GeantV is able to detect the topology of the machine behind, and basically it's able to allocate the resources in terms of pinning threads and pinning memory to the resources according to topology. And we have tested that this brings real benefits, which, I mean, if you try to run the same program on a machine having 2 NUMA nodes with 8 threads, and you are trying to write only 8 threads a given time, we have tested that NUMA awareness can bring you up to something like 9%. And this is done behind your back. You don't have to do anything as a user. I mean, it's just a framework that figures it out. Now, compared to the previous version, this version really came with very large improvements. So comparing the old and new version of GeantV, just showed the improvement between 40 and 80%. I'm not going to show now detailed comparison in performance with respect to Geant4, simply because they depend on many parameters. They depend a lot of the geometry setup, if you are including vectorized components or not, and so on. So we are planning to have a very detailed benchmarking and comparison with the Alpha-Release. In terms of physics, the Alpha-Release is aiming to deliver a full electromagnetic shower, initially only in scalar mode, because basically all these models were developed based on primary models, so on theoretical models. And these features of these models were checked for consistency with the Geant4 version, and if needed, corrections were backported into Geant4. So now the features that you're going to see in the alpha version is basically most of the models, except a few of them, such as annihilation or coherent scattering or energy loss fluctuation, which are not at this very first stage in a critical path of being able to test the product. Now, in terms of validation, we have done thorough validation, as you have heard from the Lee's talk, that really we want to be able to test for each component when we enter a new physics model in the game. We want to make sure that this is fully validated against Geant4 or data if it's about a new physics model. And really, we have tested. We have several setups testing with starting with thin layers, going through semi-infinite blocks, and then more complex setups like multi-layer target, where you test features of multiple scattering, or even the Atlas simplified sampling calorimeter. And the differences that we see are at per mil level. So really, we are aiming to delivering high-quality physics models. Now, in terms of user interfaces, that you may have taken this as a limitation from the previous talk, Lee's talk, that it's kind of complex for experiments to migrate. What we're trying is to demonstrate it is not that complex. Of course, there are changes that are needed in the user code, but those changes are not dramatical in the sense that we can do much more complex things in going towards high luminosity than this. Okay, that's what I'm trying to claim here. And of course, there will be lots of similarities with Geant4 in terms of configuring the setup, having a user detector construction, generators, scoring interfaces. But there will be also new features, because we will have concurrent scoring, limited number of events in flight, We will have multi-particle interfaces indeed that have to be dealt with. But GeantV will come with support in terms of examples demonstrating efficient data access patterns in this new environment, let's call it. Services like on-demand merging services for data, hit factories, concurrent I/O, and so on and so forth. This is just to give you an example on how basically the user life is made easier by having, because the user will need to have data per event, but also per run, and so on, since there are many events in flight. So basically, you want to make invisible for the user that he's running in an environment with n threads. And we are doing this by, for instance, providing a mechanism of whiteboards, which are data attached to every task or thread which is in flight, and which grants the fact that that data won't be accessed by more than one thread at a given time. And with mechanism and interfaces to attach user data to those task data, okay, first to register them and getting a sort of a grab of a handler, then attach them in a single method, which automatically will create and attach the data to the task data, and then being able to score based on this data, so to retrieve the data for each running thread based on the handle that you have on a single handle. So this makes the programming, if you look at the examples, very, very simple, and it really hides the complexity of having to deal with many threads. Now, of course, this will be sustained by a lot of user examples, where you have not only the implementation in GeantV, but also the implementation in Geant4, so that people will be able to see the difference. Now, I'm going just to flash these slides about some other R&D, because the R&D doesn't finish here. We are coming with a release, but the R&D goes on. So there are several ongoing sub-projects, like the inference from gun-based models for calorimetry fast simulation that you will hear about from Sophia in the second part of the afternoon. But also we are looking into something like HPC mode, being aware of the gains that you have by having a scheduler in the game, by knowing the resources of the system. Why not try it in a HPC environment in order to try to cut down the tails? In the sense of scheduling the work from the application and trying to, beyond optimizing the work per machine using topology discovery, try to handle uneven loads, policies for work redistribution in case workers go away, resilience to hanging on dead workers, and things like this. And we have really encouraging results in the sense that if you are in an environment where you have load imbalance, just having a data level parallelism will generate you a much bigger simulation time than being in a regime where you have a scheduler which is aware of the load and is able to load balance the resource that you have lost or that it became slow. Okay, so this is just as an outlook. GeantV developments are really on a tight schedule towards the end of year release, and we have a program of work which is really focused on releases now. Now, most of the components are ready, like the core electromagnetic physics and so on, but we still have few on the pipeline, and we are sure that we are going to be able to deliver by the end of the year. And the main feature that will be, that will be shown in the alpha is electromagnetic shower physics. And this will deliver only part of the design performance, but it will deliver mostly the interfaces so that the users will be able to test GeantV. And that's very important, because that will give the community a real feeling on how difficult or easy it is to use GeantV and what are the benefits out of that. And as I was saying, there is still important R&D ongoing, and yes, we have to go on.
I want question concerning the user interfaces you're describing. The GeantV is also going into an event parallel, or there's an event parallel version of GeantV available. How much different would be your interfaces to this version of GeantV?
Well, it's hard for me to say at this point because now basically the change of interfaces will not be directly reflected. It will be the fact that you will have to handle a vector signature in terms of the input. So of course, in GeantV, they will have a different input. In our case, tracks are carrying all the state information that is needed by the user to do scoring, for instance. Okay, so we are going to send the vector of tracks to the user, right? In case of GeantV, it will be sort of different. Now, what will be also different will be the in-memory representation, because in our case, dealing with multiple events in flight means we are trying to limit the number of events in flight. So basically, the user will get a number which will be the maximum number of events in flight. So we'll have to book data according a slot number, which goes to this maximum limit. Okay. So this has some sort of impact of how the user will have to organize the user data. And I guess in case of GeantV, it's going to be the same, because GeantV, you cannot afford as well to have infinite number of events in flight, or too many. So I'm guessing that from this perspective, which is the most critical part for the user, which is the data design for dealing with multiple events in flight, things will be kind of similar. Well, it's going to work so first what we have on the pipeline, and it's not yet there, but we really hope that it's going to be there by the end of the year. It's an interplay with CMSSW, in the sense that CMSSW is going to be is a task-based framework, and GeantV initially was not task-based, but was really statically thread designed, and we have redesigned it to be task-oriented, but now we are really working on this interface to work, so to make sure that in the context, for instance, of CMSSW, GeantV will be able to be callable. Like I'm grabbing events in different tasks in different pipelines, and then I'm sending them, I'm putting them into GeantV to simulate. Then I come back when GeantV finishes, and I do digitization or reconstruction on my side, the experimental side. So we want to have this in place, and we also want to have these very detailed examples a la GeantV, because GeantV comes also with lots of user examples, so that it demonstrates the usage of the thing. I mean, a user would just come, grab a thing, put his own setup or her own setup, and then go on further. Yes, that's the idea. Yes.